We studied almost entirely the subject of magnetostatics, in other words, steady currents, and we've only so far studied the Maxwell equations in two approximations: electrostatics, magnetostatics, and the dB by dt and dE by dt terms that we know are there in the full set of Maxwell equations we've not studied yet. But that's precisely what we're coming on to. And the breakthrough discoveries were made by Michael Faraday, and there's a picture of Michael Faraday. He lived from 1791 to 1867, and as we know, Maxwell wrote his greatest discovery, one of the greatest discoveries in physics, as a personal letter to Faraday. Now Faraday, it was reckoned, again this is a sort of new scientist level of looking at things, if he'd been a 20th century physicist, might have won 6 Nobel Prizes, one of which would have been for discovering electromagnetic induction, which we'll be studying this week. Another one was electrochemistry, which is now used massively in electroplating. He discovered the whole of my own research field in colloid science when he discovered the gold sols in the middle of the 19th century. And to give encouragement, particularly to those of you who occasionally struggle with the maths, Faraday couldn't do maths at all, really. He did everything by a kind of intuitive brilliance, and it was Maxwell who turned Faraday's intuition about induced currents into a quantitative differential law that was, in a sense, the breakthrough. So we kind of moved on. This quote here is it's actually from Volume 1 of the Feynman Lectures, and he starts off with Volume 1, Chapter 1, Section 1. He emphasises this. The Maxwell equations are beautiful, but they're not true because they're beautiful. They're true because they agree with experiment. And towards the end of Lecture 5, I mentioned one or two purely experimental aspects of electromagnetism, exactly so that we don't forget we're studying an experimental subject. So figure 7, I mentioned again, we're not going to do much on the force acting on the charges, but in a modern way we can certainly understand exactly why, if we put a current on a wire, well, there must be some charges in motion. The drift velocity of the electrons is how we'd now interpret it. And so if we've got a current in this direction and a magnetic field in this direction, we get a force on the wire in this direction, of course mutually perpendicular in this case, the 3 vectors as expressed by the cross product. You know, this is a fact. The wire really does move. So we're actually looking at experimental facts. Likewise, of course, I mentioned that in electrodynamics, action and reaction are not always equal and opposite, but in a simple case like this, we can indeed interpret what's going on in that way and say, well, likewise, if there's a current on the wire and there's a force on the wire, there's a force in the opposite direction on the bar magnet. And this is, in a sense, precisely how we measure. Coming to that in slightly more precise detail, how we measure currents. In fact, the measurement of current is from 2 parallel wires. Now, again, where the experimentalists have sort of won in this sense, of course, it's a cooperation throughout between experiment and theory, is you might have wondered, well, why is the amp the SI unit of electricity? You would think it's surely going to be the coulomb. That seems to be more fundamental. But actually it's very difficult to do an experiment to measure the coulomb, because once you've charged, let's say we've charged an object up, even in an ultra high vacuum there's going to be a few gas molecules knocking into the surface, carrying charge away. So it's actually quite difficult to set up an experiment with constant charge, because you've always got some finite number of collisions with gas molecules, and so as you're doing the experiment, your charge is starting to sort of drain away. from the surface. However, there's no charge involved in this experiment. These two wires are not charged, they're just carrying a current. They're both neutral. Sure, there's a drift velocity of the electrons past the iron cores, but that is a situation where you can set up a much more accurate experiment. And so that's why the amp is defined as the fundamental unit, because it's much easier to measure. And again, you'll have done this in EM1, that you define the ampere precisely so that if you have two wires that are infinitely long, infinitesimally thin, you know, the usual physics abstractions, and in a vacuum, then 1 amp is defined as the current that produces an attractive force of 2 × 10⁻⁷ newtons per metre along the length of the wires. The choice of this apparently bizarre 2 × 10⁻⁷ will become clearer when we've done the unification theory. So I won't sort of justify that yet. You'll see why that's the case later on. So we looked at those three things towards the end of lecture 5. The other ones that I kind of missed out in the course so far, there was the figure 10 here, and that one is, again, it's absolutely the same as figure 7, and that is deliberate. And there's figure 7, there's figure 10. If you superimpose them, they should superimpose just about. Exactly, I wanted to emphasize throughout that although having a bar magnet's an apparently static situation where there are no charges in motion and we still get a magnetic field, that the bar magnet actually behaves exactly like a coil of wire. And it's indeed the final lecture of the course to explain that. But you can take it that, in effect, it's charges in motion which produce magnetic fields. Now, we now come on to lecture, the real material of the lecture, in a sense, in that, again, the view graph monster's been at work here. Figure 11 on the electric motors. I sort of disappeared for a minute. There it goes. Well, now, just with these simple magnetostatic ideas, we can say that there's going to be a huge advance in not only physics and technology. So here we've got a current passing into a coil, and in the upper part here, the current is flowing in this direction. The magnetic field is north-south in this direction, and we get some lateral force on the wire. As the current completes its loop, in this part, it's going in exactly the opposite direction. The magnetic field is still north-south, if we make the arrangement in this way, and the force is in the opposite direction. So we exert a torque on the coil. It turns. And as soon as this effect was discovered, about 1820, people started to design simple electromagnetic motors. And of course, at first, these little twitchings of current-carrying wires in magnetic field would hardly have believed that they were going to replace the steam engine within half a century, and that these little feeble twitchings of wires in fields would completely change the era of technology into our modern era of electrical technology from the steam-driven technology of the time. Once you get to this, though, you've got to now consider something different, because as the coil is rotating, the amount of magnetic flux going through it is changing as a function of time. If, again, let's make we've got a magnet here producing a field that's vertical. If the coil is in this plane and all the flux is going through it, there's a lot of magnetic flux going through the coil. But as it rotates, if the coil is like this, there's no magnetic flux going through it at all. So we're now moving on to a completely new kind of phenomenon, and that's of the dynamic effects. So again, figure 12 is the one that this was, if you like, now we've gone on another 20 years. We're now looking at the discovery of Faraday in 1840. Ampere's law was 1820. We've already gone from the mid-19th century in electrostatics. We've done magnetostatics. We're now moving on to discoveries around 1820. And it was like very natural for the early investigators to think, well, if currents make magnetic fields, and currents are just electric charges moving, do magnets make, if currents make magnetic fields, which that was already known, do the magnets make electric fields? A kind of, you think, well, there's going to be some reciprocal relationship. And what Faraday discovered that is only when you have a changing magnetic field that you get electric effects. And our first discovery is that if you move the wire, you hold the magnet still and you just wave the wire. Remember, the magnet's producing some magnetic field lines. Oh, that one should be going straight up. Some magnetic field lines, and this wire's cutting the magnetic field. And that's the way Faraday thought. He wasn't thinking of vector calculus. He was thinking we're somehow cutting field lines, and that's the important effect. And when you move the wire, then if you move the wire one way, the galvanometer will twitch one way. You move it back the other way, the galvanometer twitches. But as soon as you restore the situation to a static one, there's no current. It's not just that the magnet hold it there, doesn't do anything. So this is, and you say that this current's induced. Incidentally, the galvanometer itself is using the principle of, if you like, the motor, in the sense that you imagine that coil which we showed as a motor is now just a little loop of wire and it's suspended on a thin quartz fibre. Well, if it's in a strong magnetic field, even a tiny current will make the wire move. And when I was a student, we had a thing called a ballistic galvanometer, and you could actually see the insides, and what you could see was that there was a little mirror attached to this tiny little circuit, and when a current passed in it, there was exactly the torque that we described. The torque just slightly turned the mirror, you shine a beam of light onto it and back out, well, of course, you observe the light move, and you have a graduated scale, and you measure the current. And voltmeters and ammeters work on the same principle. So that's what's going on inside a voltmeter and an ammeter. These days, we just read a digital output. We just plug it in. Oh, yes, that's a current of 2 amps or whatever. But what's going on inside is actually using the magnetic effect. So Faraday's complete discovery was threefold. Secondly, if you move the magnet next to the wire, you also get this twitching of the galvanometer. You get these so-called induced currents. They're induced by this motion. And we'd understand that these days, of course, from a relativity argument. We'd be absolutely amazed to think otherwise, that if I moved, instead I held the wire still and I waved the magnet next to it, if I didn't get the same effect. That at the time, though, was regarded as a completely independent discovery. Remember, relativity theory came from electromagnetism, so this was not so obvious when the discovery was made. But then also, and perhaps the biggest breakthrough of all, Faraday discovered that if you have a changing current in a nearby circuit, you also get an induced current. And again, we might expect that. Somehow, we don't need to be too precise at the moment, there's obviously a dB by dt. The magnetic field will be experienced by the wire will be changing either if we move the wire or if we move the magnet. But this is now slightly more subtle. This was the third of Faraday's discoveries. And again, it's in here somewhere. Here we go. The third discovery was that if you have a coil with a current in a second coil, if the first coil is moved or if its current is changed, then we get an effect. So here, if I'm just passing, and just to emphasize again, if this battery has been connected for a long time and there's a steady current flowing around this circuit here, absolutely nothing whatsoever happens in this circuit. However, if I disconnect the battery, well then there's a di by dt, and we know, we've done the solenoid, we know that the magnetic field strength is just going to be mu naught number of turns per unit length times the current. Well, obviously, if I change the current, I change the magnetic field. So if I disconnect the battery and the current drops in this circuit, it induces a current in the other circuit. Likewise, if I then reconnect the battery and the current and start a changing current, again the galvanometer, again it will deflect in the opposite direction, responds. So this is the three great discoveries made by Faraday. So I'll start with that. You know, this is starting off very much with grounding it in the experiment. So in 1840, we've leapt forward another 2 decades now, Faraday discovered that electric effects of magnetism only exist when a magnetic field is changing. Emphasize this changing. A steady current emphatically does not produce any electric effects at all, but a dynamic magnetic field, doesn't matter how we produce the dB by dt, produces electric effects. So I'll write out his complete discovery, and this is illustrated of course in see figure 12 and figure 28. So Faraday's complete discovery, as I say, in the modern era, we wouldn't probably regard these as independent discoveries, but they were certainly regarded as 3 independent discoveries 170 years ago. So his complete discovery was that, and again, you've heard the word, and we're going to come to, of course, define it in a much more quantitative way in a minute. Electromotive forces, always abbreviated to EMFs, can be generated in a wire in 3 ways. Only 2 of them are illustrated in the figures, but it seems a bit trivial to have a separate figure to say if I wave the wire I get the effect, if I wave the magnet I get the effect. It's clearly, we would now understand that as the relative motion. 1, by moving a wire near a magnet. Now these are the raw experimental facts. 2, by moving a magnet near a wire. That also works. And 3, it's now got the posh word actually of Faraday switching, is that this third effect, of course this circuit doesn't have to touch this circuit at all. There can be a vacuum in between them. There's absolutely no wires connecting this circuit to this circuit. It's just this circuit produces, it's a solenoid. As I put a current through it, it produces a magnetic field. But it's its field lines, its B field lines then change in this circuit, but there's absolutely no connection between these 2 circuits. And again, it's called now a Faraday switch. You can switch a remote circuit on and off simply by this effect. So by changing a current, again, emphasize this, in a nearby wire. So these are 3 great discoveries that were made. Now, what do we mean by an EMF? We're saying that actually it would be better to sort of talk about induced EMFs, but normally we talk about induced currents. What is the EMF? And that is the next thing where we now get slightly more mathematical, but it is a pretty straightforward definition. I mean, intuitively, it's the kind of net push on the electrons integrated once around the circuit. Something is obviously pushing the electrons around the circuit. And we tend to think, because the first thing we learn is Ohm's law. Incidentally, after 36 lectures in this course, we'll have absolutely no insight into Ohm's law whatsoever. It's much too hard for us. Now, this is a property of matter that's an approximate equation, and indeed doesn't apply to superconductors, doesn't apply if you vary the temperature and so on. And perhaps another irony is that, you know, I'm sure you, me and everybody else, the first circuit we ever did was connect up a battery to a lamp, and we'll get absolutely no insight into that at all. But one of the things I want to emphasise is that clearly this electromotive force is doing work on matter. It's got units of volts. We'll come to this. We shouldn't really describe it as a voltage, but let's just say we take for it electromotive force seems to be always written in a Greek capital epsilon. Clearly, if we've got an Ohm's law type circuit, and you know we can make them, of course if we have an EMF we will get an induced current. So, but the more fundamental thing than the induced current is the induced EMF. That is something that we can and will calculate for first principles. And although it's units of volts, we won't be able to describe it by a potential, just like we couldn't describe magnetic fields by a potential, because this wouldn't glow. Let's say this is a tungsten filament. Well, look at the bulb on the projector. The field is clearly doing work on matter. And so this is a very important point. The EMF is the net force, if you like, on a unit charge tangential component going around the circuit it's pushing somehow electrons around the surface integrated once round the circuit. So, and again, this is now, if you like, due to Faraday. It's all very well. So in other words, what we're saying, put it in equation form, this EMF is the line integral around a complete closed path of E ds. Faraday just had this intuition that electrons were being pushed around the circuit. Now, in a more sophisticated way, we would describe this as the line integral of the tangential component of the electric field, E dot ds, integrated around the closed path. So again, if we go right back to the beginning of the course, this was for electrostatics. And for electrostatics, of course, we can define a potential. We start at point A, there's some potential phi at point A. We end at point B, there's some potential phi at point B. And this force is equal to Q times the electric field. So if we have a unit charge, this is the force is the same as the field. But of course it follows from that in an electrostatic field that if I go all the way round, if I do integrate round a closed path, well, phi A minus phi B, if phi A and phi B are the same point, is naught. Now this absolutely isn't, and this is why, I'm sorry I'm probably being a bit boring to say the same thing about 3 times, 4 times is that people get misled because they think, oh yeah, it's measured in, oh well, AC mains, it's 240 volts, isn't it? You know, it's like a voltage, that's a potential. It's got the units of a volt, but it is emphatically the dynamic electric field produced by a changing magnetic field. The electric field which comes from dB by dt absolutely cannot be described in this way. The light wouldn't be on otherwise. Where would I be getting the energy from? I'm drawing energy from the electric field in order to heat the filament. We'd solve the world's energy problems if I could just, you know, like get it for free. I don't. You know, there has to be a magnet turning in Selby Power Station to keep this going. So again, it's such an important point. I'm going to put a note on it. Note that the electric field due to a changing magnetic field is non-conservative. And this is quite unlike the electrostatic field. And strictly speaking, we should never describe it in terms of a potential. Of course, when we're doing engineering problems and we're along, like the huge magnet that's spinning next to a coil in Selby Power Station that is providing us with all the electricity in this room, is a long way away. And we're far from the electric field, and we can, if you like, in a crude way, treat it like it was a 240 volt AC voltage, but it is never to be described in the simple way of an electrostatic potential. It's simply not possible. So how do we describe it? It's all very well saying we're producing this EMF, but of course we want a quantitative rule. And the amount of EMF, we want to know how much, we want to know how big this EMF is. So the amount of EMF, and again, I'm going to use this curly, it's a funny symbol, curly Greek epsilon. The amount of EMF is given by a simple rule discovered, of course, by Faraday, and it's known as the Flux Rule. And the Flux Rule says E is equal to minus d phi b, straight back derivative, because it's just a time-dependent problem here. So we'll have a curly time derivative soon when we have to consider space and time in the same problem. Oops, excuse me, got that going the wrong way. Let's move this up a bit. And where, again, I'll just use boards are probably easier like this, where phi b is the magnetic flux through the circuit. So again, you'll have studied that in EM1. And it's perfectly true, but we're now again going to be much, with our new maths, a lot sharper in the way we look at the flux rule. So the EMF, we know we can now make a more crisp definition on the left-hand side. It's a line integral of the electric field integrated around a closed path. Well, the magnetic flux is, of course, phi b. The magnetic flux is the surface integral of the normal component of the magnetic field. So, for example, let's say that I've got a magnetic field going from the floor to the ceiling. You know, somebody's whacked an enormous north pole in the floor, an enormous south pole in this evening, and I've got all these field lines. Well, if the circuit is this, and I'm just considering a current flowing around this ostensible metal circuit around the outside, got a bit of imagination, I know it's only a piece of paper. Well, the magnetic field is now at a maximum because it's B dot N. The normal component to this plane is clearly the same as the magnetic field. So that would be straightforward. But obviously, this has got no magnetic flux going through it whatsoever. And indeed, at any intermediate position, I will have B times the area of the circuit times the cosine of the angle between the surface normal and the magnetic field. So we've now got Faraday not only discovered the existence, if you like, of EMFs due to magnetic fields. He had this idea that you were cutting through field lines. Maxwell, who was, of course, a great genius in maths, realised that this was the EMF, and he realised that this was the correct vector integral way of representing the magnetic flux. You'll notice in the equation there's no constant of proportionality. We've now discovered, remember, when we had electrostatics, we were relating the electric field to charge. When we had magnetostatics, we were relating the magnetic field to currents, and there were constants in there, epsilon naught and mu naught. This is obviously an extremely intimate relationship now between electric and magnetic fields. This isn't saying that EMF is proportional to the rate of change of magnetic flux. Come to the minus sign in particular tomorrow, which is necessary from conservation of energy. It's saying the EMF is the rate of change of magnetic flux. There's no constant. The minus sign is also important. So we can now combine these equations in a straightforward way. Actually, let's use this side. So we now got a good way of defining the EMF. We've got a good way of defining the magnetic field. So combining equations 8.1 to 8.3, we have that the line integral around any closed path of the tangential component of the electric field is equal to the negative rate of change of the magnetic flux through the surface, where again S is any surface bounded by the loop gamma. So we've now got a much sharper, that is the flux rule in a kind of crude way, it's true. This is what's called the vector integral form of Faraday's law. Faraday would never have written it in that way. He didn't understand vector integral calculus, differentiation, all these, advanced mathematical concepts. Maxwell, however, framed this idea of the E is minus dB by dt in this way. Now, if you're very sharp at maths and you followed the course closely so far, you'll probably see what's coming, because we can now apply Stokes' theorem. So applying Stokes' theorem to the left-hand side of equation 8.4, we have that the line integral of the electric field around any closed loop is equal to the surface integral of the normal component of the curl through any surface bounded by that loop gamma. So, and again, remember, this is absolutely pure maths. This applies to any vector field C. Its line integral around a closed loop is the same as the surface integral of its curl, normal component integrated over any area bounded by the loop. And because it's true for any vector field, it's certainly true for the electric field. So I won't even give that an equation number because it's pure maths. There's no physics in this at all. The physics is the flux rule. But when we combine this result with this result, we get, therefore, the surface integral of the curl of the normal component of the electric field is equal to the, negative rate of change of the normal component of the magnetic field. And now this part, I don't think there's any kind of a priori justification other than it always works. You've got onto the idea now in quantum mechanics of how commutation, think like position and momentum operators don't commute. Well, space and time operators always do commute. So I can take the spatial surface integral, and now, of course, because I've written the time as a partial derivative because I'm thinking in space and time rather than in the simple flux rule. Sorry, these boards aren't great. That's, of course, a dot product here, and this is a dot product here, is that I can take the time derivative either inside or outside the integral sign. So the time integral, the time derivative can be taken inside or outside the spatial integral. So this always works, and we'll use it quite a lot in the course, and we can therefore have that the surface integral of the normal component of the electric field is equal to the surface integral of, and again, of course, I can take the minus sign wherever I like, minus dB by dt dot NdA. So this, again, we're just doing a little bit of maths, but what we're now saying is, and again, we've used this before, but if this integral over any arbitrary surface, if integrating the normal component of this vector over any arbitrary surface is equal to integrating the normal component of this vector over any arbitrary surface, the integrands have got to be equal to each other. Therefore, or equating the integrands, and we're doing, like what took, people decades to work out in the middle of the 19th century. We get to this beautiful result that the curl of the electric field is minus dB by dt. And let's number this one up to follow this one. This is called the vector integral form of Faraday's law. And equation 8.5 is the differential form of Faraday's law. And you can see we're now really starting to get there. We've already studied, again, this is just, make a note if you like, we studied the static approximation where del, and I emphasise that this equation is always true. Electrostatics And all that safe world of conservative fields and potentials was only true when this was naught. But we now know, and Faraday's law, it turns out, experimentally, is always true. We've now got the complete expression for the electric field in any circumstances, whether it's produced by a static charge distribution or a dynamic magnetic field. So we have got those pieces. When we did magnetostatics, we had this equation, and I emphasise that's always true. There's no magnetic monopoles, magnetic field lines don't spread out from a point. And we had Faraday's law, mu naught J. Now, we've now got to the stage of being able to understand all of the pieces in the Maxwell equations except one. Before we can understand why we have got a plus mu naught epsilon naught dE by dt, which was discovered purely theoretically by Maxwell and turned the fourth equation into the Ampere-Maxwell law, we've got to do a whole lecture on charge conservation, which will come up later in the week. So before we do that, there are, of course, absolutely massive consequences of Faraday's law. We'll come back to some of them at the end of term, because I want to put, you can imagine a lot of it is to do with energy. And we'll come back to it at the end of term. What I want to do at the moment is just outline some of the consequences of Faraday's law. We'll do 3 very specific examples tomorrow where I'll apply this vector integral form. We'll apply that. We'll do 3 very detailed examples of how this works in the lecture tomorrow. And then we'll do charge conservation, which will explain to us why we get the Ampere-Maxwell law. Then we'll go on to the unification theory, which will be entirely in terms of the differential equations. First, however, let's just look at some of the many consequences. Well, the invention of the telephone, that was a fairly important development in the human communications. So it's a lot faster than sending a letter by horseback, and or even by and by this time by railway. And although like our modern mobile phones are very, very sophisticated devices, which incidentally use the electromagnetic waves we're coming on to, this is like the original Alexander Graham Bell telephone, but the principle hasn't changed. So there you are, your voice, you make a little bit of sound pressure. Now what we design is that your sound pressure will move this iron disc. And then this iron disc, again, we'll come to the properties of iron later, but it's not hard for you to imagine that as this iron disc touches this, then it changes the magnetic flux in a coil. And because there's a changing magnetic flux in the coil, and it produces an EMF in this copper coil, off goes a representation. Now, as your voice makes the vibrations and things back in, out, of course, very rapidly, as you're making the vibrations, you then simply make an electrical representation of them, because the dB by dt that's produced by this sound pressure on this iron disc, and the flux is concentrated by having permanent magnets inside your speaker, then that sends off an electrical representation. Off they go. They might go under cables to New York or wherever now, so Tokyo. You will, at the other end, you have a similar device. But now at the other end, it's an identical device, but it's reciprocal. Your EMF now produces a current at the other end. Now the current at the other end changes the magnetic field here, so it changes the attraction of these magnets to these magnets and makes them wobble at the other end. Oh yeah, hello, yeah, we're having a great morning here. Martin's lecture's a bit boring, he's rabbiting on as usual, Stokes' theorem again, and so on. But you can hear it anywhere in the world. So before we go on to the sort of deeply mathematical side, I'd like to make a bold but I think true statement. Induced currents are the basis of all electrical technology. I don't think there's any reason to take back the all. It's the dynamic effects that are important. And there could be so many examples. Let's just say examples include A, the telephone. This one's illustrated in figure 29 of the course handout. So we've got the telephone. I've already mentioned it in a different context. Very straightforward, the Faraday switch. Because the changing magnetic flux means that you don't have to have any direct connection between the two circuits, I can clearly, again, we're coming to how the AC generator itself works in a minute. Obviously, if I have got an AC current passing through here, the current is growing, decaying, it's sloshing backwards and forwards. There's clearly a dB by dt. Because this circuit senses the magnetic field lines are permeating all space, of course it produces a changing magnetic flux in this circuit, no connection whatsoever, and we light the bulb in this circuit by switching this one on and off. So B, just a bit inconvenient, I've got to go all the way, anyway, I need some exercise, so it's nice to have the board far away. B, the Faraday switch. You can switch a circuit on and off at long range. And, well, I'll keep going because I think, you know, let's put it all together. This isn't so much the next one, an application, but just something that a lot of you have probably seen. How many people have done UCAS Day here? Come on, you must have at least done it once when you came. Did you see the Thomson jumping ring experiment? Anyone seen that? I mean, and this is again an example of, if you like, a Faraday's law effect. We've got an AC generator here and some kind of switch. We can switch the circuit on or off. Now, when there is if you like, this will this will become let's say, for the sake of argument, that the changing electric field at some particular time has made the North Pole at this end. Now, again, this ring is emphatically, it can jump in the air, it's certainly not connected to the rest of the circuit. And this is connected to why we've got the minus sign in Faraday's law. That's saying that the induced EMF opposes the flux change. If the magnetic field's growing one way, the EMF a bit anthropomorphic, but pushes it the other way. So when this becomes the North Pole, remember this is a dynamic effect, it's an AC generator. There's an induced current in this one, but the induced current in the conducting ring makes the bottom of the ring a North Pole at the bottom and the top of the ring a South Pole. And the North Pole here and the North Pole here repel each other, and there's a force and the ring jumps into the air. So when you connect the circuit, Faraday's law is the basis for the Thomson jumping ring experiment. Another one, to say way beyond what you might consider with Ohm's law, let's say we had a perfectly conducting plate. Well, again, here, if we try and move this thing towards the perfect conductor, of course, if we move this magnet, it's drawn here as an electromagnet, but it wouldn't matter. If we try and move this magnet near to the surface, well, as we move it, this thing's conducting. So currents are induced in the plate, and they must be induced such that the top of this is the negative sign, that the top of the plate becomes the North Pole and the bottom the South Pole. And so again, you can suspend a magnet over a perfectly conducting plate because you induce currents in the plate that oppose it, and it will just hover in the air. And indeed, many of you have probably seen this as well on UCAS days. It's called the Meissner effect. And we don't have perfect conductors, but we do have superconductors. Incidentally, they're not the same thing, as you'll come to see later on. But for the time, you know, you kind of think, oh, perfect conductor, superconductor, there's no resistance. They're not quite the same thing. But certainly, we can make superconductors. And in particular, again, you try and move a bar magnet towards a superconducting bowl here. Well, it makes little currents flow round in the bowl, and that turns this into a north pole, and at this end into a south pole. So the magnet hovers. And a very nice way of doing the demonstration is that you first of all have the superconductor at below liquid nitrogen temperature, where it is a superconductor. You then slowly let it warm up through Tc, the critical temperature, where it becomes a normal conductor. And when it's a superconductor, the currents will just flow forever. So the thing will just hover there forever. So it's called the Meissner effect after its discoverer. But if you then let the bowl warm up, these currents now experience resistance. When they experience resistance and the energy drains out of the system, then the thing will sink when it's taken up through Tc. So all of that, again, this is because as you try and move the magnet towards the bowl, you induce currents. And on that theme, again, you might have seen this done, is that if you try and swing a metal plate through a magnetic field, it has braking forces. And again, it hasn't made so much progress, but quite a lot of people are doing research on electromagnetic clutches and brakes for cars. For example, Professor O'Grady, who gives a fourth year magnetism course here, has done a lot of work on ferrofluids. And now some very expensive, like a top range Mercedes, if you just tread on the brake pedal, what brakes it is the properties of a ferrofluid. It's not brake through mechanical friction at all. And again, here you can generate, again, this is going to be one of our example type calculations tomorrow. You can generate a braking effect because, and it's shown in more detail in figure 35, is that, and again, the eddy currents flow round in little circles. Again, you can, it's the curl. Remember, the magnetic field's going from the north to the south pole, and our usual physicist way, let's say there's a load of perfect straight field lines. As this metal plate tries to swing between the poles, there is the dB by dt is going in this direction, so the curl is in this plane, and sorry, not the curl, that's the usual mistake that everyone else makes that I'm not supposed to. The circulation of the electric field is non-zero, and that drives circular currents round through the plate. And of course, if this is just a normal conductor, these so-called eddy currents will precisely dissipate energy, V equals IR approximately, and the thing slows down. The energy's got to come from somewhere. And another experiment that's very, very beautiful is that if you make this of a superconductor and you do the same experiment, well, then there's nothing to dissipate the energy, but the force is still there, and the force still opposes the motion, and you try and swing it into the magnetic field, it just bounces back out completely, comes back out to the same height. And then, of course, under gravity it falls again, but as soon as it gets into the magnetic field and starts to cut the magnetic field lines, the eddy currents go in such a way, as we mentioned this several times, this face of the plate will get a south pole as a result, this place will get a north pole, it's repelled, and it bounces back out. Again, same idea as with the Meissner effect. If you then let it warm up, it goes in. And it's it's actually even more amazing when it's an ordinary, because it's not touching anything, but it is just, you see it break down like you've dropped it into honey. From air into honey, the plate, sort of like, have a great big metal plate goes whoosh, and then as it hits the field, it's like it's got this braking force on it. So, etc., 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 etc. Tomorrow we'll do some real quantitative examples on how it works.